Welcome to today's Explainer. We're diving right into the unseen physical forces constantly pushing and pulling all around us. Specifically, we're looking at the fascinating mechanics of fluids. Whether you're splashing around in a pool or just sitting in a chair breathing the air, you are constantly interacting with fluid mechanics.
Have you ever noticed how you can easily lift a heavy friend in a swimming pool, but you'd struggle to do that exact same lift on dry land? Or how about this? How does a tiny tap of your foot on a brake pedal manage to bring a massive speeding car to a screeching halt? These might sound like totally unrelated scenarios, but they're actually driven by the exact same invisible rules.
All right, let's break this down. It all starts with pressure. Simply put, pressure is just the amount of force applied over a specific area. Think of the formula, P equals F divided by A. But here's where it gets really interesting. Pressure behaves completely differently depending on whether a fluid is open, like a rushing river, or enclosed. If you push on an open fluid, the water just splashes out of your way. But if you trap that fluid in a closed system, applying force does something absolutely incredible.
When a fluid is trapped in a closed container, its atoms are still bumping around in there. Because of this, if you squeeze it, they transmit that pressure equally to every single part of the fluid and to the walls of the container. This is a brilliant concept discovered by Blaise Pascal back in the 1600s, which is why we call it Pascal's principle. The absolute key word here is undiminished. That change in pressure doesn't weaken, it is transmitted undiminished everywhere inside that closed system.
So, what does this actually look like in real life? Let's trace how a car's hydraulic brakes use Pascal's principle. You press the pedal with, say, 100 newtons of force. That pushes on a small master cylinder, creating pressure. Thanks to Pascal, that exact pressure travels undiminished through these crazy, curvy brake lines right to the wheels. And here's the magic trick. The cylinders at the wheels have a much larger area. Since pressure equals force divided by area, if the pressure is exactly the same, but the area goes up, the output force absolutely has to go up. The fluid acts literally like a lever, multiplying your foot tap into thousands of newtons of stopping power. Okay, time for a quick pause check. I want you to pause this explainer and think about a tiny jumping spider. These little guys can leap 25 times their own body length. Based on what we just talked about, does this spider need some kind of massive, motorized pump hidden in its tiny body? Or does it just use enclosed fluid and varying areas? Pause and think it over.
All right, you back? The answer is, the spider uses internal hydraulics. By pushing fluid from a smaller area into a larger area within its legs, the pressure transmits undiminished, multiplying the force and launching the spider right into the air. Fun and slightly creepy fact, this is exactly why spiders curl up when they die. They literally lose that internal hydraulic fluid pressure.
Okay, so we've totally mastered the squeeze of enclosed fluids. Let's switch gears to open fluids and figure out why you feel so incredibly light lounging in a swimming pool. You know that feeling when your arms and legs suddenly feel like lead the second you step out of the water? That's because while you're submerged, the water is physically supporting you.
Now, where exactly is that support coming from? Well, in an open fluid, pressure naturally increases the deeper you go down. Because of this depth difference, the water pushing up on the bottom of you is always stronger than the water pushing down on the top of you. The horizontal forces pushing on your sides, they just cancel each other out. But that vertical difference creates a net upward push. We call this the buoyant force.
So just how strong is this buoyant force? According to the ancient Greek mathematician Archimedes, this net upward push is exactly equal to the weight of the fluid shoved out of the way when you get in. Think about it. The space your body takes up in the pool used to hold water. That specific volume of water had a weight, and it was supported by the water underneath it. When you jump in, the surrounding fluid pushes up on you with that exact same amount of force. That's Archimedes' principle in a nutshell.
Let's test this with something extreme, just to put it into perspective. Imagine dropping a massive, perfectly solid block of steel straight into the ocean. We're talking 10,000 metric tons of solid metal completely submerged. Will the buoyant force be enough to save it from sinking? Let's trace the physical forces here step by step. First, you've got gravity pulling down. The weight of that solid steel is a whopping 98 million newtons. Now, because it's completely solid, its volume only displaces about 1,280 cubic meters of water. Based on Archimedes' principle, that displaced water pushes back up with 13 million newtons of buoyant force. 13 million newtons pushing up sounds like a lot, right? But compared to the 98 million newtons pulling down, it doesn't stand a chance. The downward weight is just way too great, so our solid steel block sinks right to the bottom.
Which brings us to our second pause check. Say you drop a lump of solid clay into water and it sinks just like that steel block. How could you make that exact same mass of clay float? The rules are you can't take any mass away and you can't change the liquid. Pause the explainer and see if you can figure it out.
And we're back. Did you get it? The secret is to mold that clay into the shape of a boat. Here's the reasoning. By hollowing it out into a bowl shape, the boat displaces a much larger volume of water than the solid lump did. And remember Archimedes? More displaced water means a greater upward buoyant force. Eventually, it displaces enough water that the upward push perfectly balances out the weight of the clay, and boom, it floats. This, by the way, is exactly how cargo ships made of thousands of tons of heavy steel can easily cruise across the ocean.
All right, this is the perfect time for some myth busting. We've talked a lot about floating, but what's actually happening when an object gives up and hits the bottom of the pool? Let's uncover the secret life of sinking objects.
There's a huge misconception out there. I hear it literally all the time. People think that if an object sinks, it experiences zero buoyancy. Like buoyancy just gave up and went home. But the truth is, the upward buoyant force is always fighting gravity. Always. If an object sinks, it simply means the buoyant force was less than the object's weight. But that upward push, it is absolutely still there. Gravity might have won the tug of war, but buoyancy never let go of the rope.
And we have solid proof of this. It's called apparent weight loss. Even massive, sunken objects, like a huge metal ship's anchor, are partially supported by the water. If you weigh an object in the air and then weigh it again underwater, it literally suffers an apparent weight loss, perfectly equal to the weight of the fluid it displaced. So if you try to pick up a heavy rock from the bottom of a lake, it feels way lighter than it does when you get it onto dry land, because the water is literally helping you lift it.
Fluids are seriously powerful. Let's do a quick recap to lock in what we've discovered today. First up, pressure is simply force per unit area. Second, Pascal's principle showed us that enclosed fluids transmit pressure undiminished everywhere, which is how we multiply force in things like car brakes. Third, open fluids push back up on objects with a buoyant force. Fourth, Archimedes' principle proves that this upward force is exactly equal to the weight of the displaced fluid. And finally, our myth busted, every submerged object feels that upward push even if it rests flat on the ocean floor.
Before we wrap up, I'm going to leave you with one final real-world transfer question. Our atmosphere, the air we're breathing right now, is also a fluid, and it plays by these exact same rules. So, based on Archimedes' principle, why does a hot air balloon float in the sky? How do the exact same principles we just applied to water allow humans to fly through the air in a giant wicker basket? Think about the weight of the fluid being displaced versus the weight of the balloon itself. I hope this explainer has completely changed how you look at the invisible forces pushing and pulling you every single day. Keep questioning, and thanks for learning with me.